As we said, we need before we go to sketch the body plot, we need to write the transfer function in its standard form. Standard form means we said all the poles and zeros should be. I mean, we need to or divide the transfer function over the poles and zeros. So we make it like s over the z1 plus 1, s over z2 plus 2. This for the numerator. In the denominator, it will be like s over p1 plus 1, s over p2 plus 2, and so on. Plus 1, I mean, all become plus 1 plus 1, same like we have here in this form. Okay. After we write this transfer function, we will come out with some of the standard parts for the transfer function. And this standard part, they have each part, it has its own individual body plot. So for example, if we have transfer function like g or h omega here, h omega, we just write j omega or h omega is the same. Okay, just we write it like h omega here is equal to 10 omega plus 1 over omega plus 2 omega plus 3. Okay, it is j omega, but just I write it for simplification omega. Okay, so this transfer function, for example, consists from zeros and poles, and also it has a gain here. So when we say the gain, it represents the value of the, I mean, the constant number here, or the magnitude of our transfer function. Can be 10, 5, 3, whatever number without any omega, without any s. So this will be represent, or will represent our gain of the transfer function. Usually we call it the gain k. So this is the first part. If there is no number here, if your transfer function directly s plus 3 over s plus 4 times s plus 5, so that means your gain here is equal to 1. There is no gain, for example. Okay, but if you have the gain value, so you need to draw the log magnitude of this gain and also the phase of this gain. So what we need to do here, I mean, in order to draw the body plot, we need to draw each part of this transfer function separately, because if we want to draw it manually by using our hand on the semi-log paper, I mean, just we draw it by ourselves on a semi-log paper. So first we need to write the transfer function in its standard form. Second, we need to split or separate each type of the elements in this transfer function and draw it alone. Then we combine our drawings or our sketch into one sketch. But if we want to draw it using MATLAB, you just write the 2-line codes for MATLAB, then the body plot will come out as output of your graph or output of your coding. Okay, so for manually drawing body plot, we need to write it in its standard form, then split it into its own or main components. For example, here we have, this is the gain, this one one component, this is one another component, this one another component, here another component. For example, if you have like 3 zeros, so you are going to draw 3 graphs for zeros. 2 balls, you are going to draw 2 graphs for 2 balls. 1 gain, so you are going to draw 1 for the gain. After you draw all separately or individually, you are going to combine or your graph into one graph. Okay, so this will be your body plot. So as you can see here, the basic factors or the basic components for every for any transfer function consists from these elements. First is the gain. This gain is a constant value. This constant value will be drawing alone or individually. Then after you have one gain, actually we should have only one gain here, because you cannot have 2 gain, because the gain is only one constant value. If you have like 5 times 7, so you are going to draw 35. Okay, you combine it into one constant number, then you are going to sketch. The second is integral and derivative factors. When we say integral and derivative factors, we are talking about the zeros or poles at the origin. That means I have the value in my transfer function, I have this element s. or I have this element here, s plus 1. I have s in the denominator, I have s in the numerator, or I have omega in the numerator, omega in the denominator. So if I have such element, it means that you have a zero or poles at the origin of S plane. That means the location of this zero or poles will be at the origin point here, at the point of origin. So here you have zero or poles. In this case, we call it, if it is zero, we call it integral. So in this case, we have either j omega, that means 0 at the origin, or 1 over j omega, so it is a pole at the origin. So in this case, I mean, each one of these form or of this factor, it has its own body plot drawing. We will see later on each one by one. The third type, which is the first order factors. That means first order factor, it can be a zero or a poles. So if it is in the numerator, it will be a zero, like 1 plus j omega here. Or if it's a pole, so it will be like 1 over 1 plus j omega. So the 1 plus j omega here will be at the denominator of our transfer function. After your, I mean, there is another representation for the sum of the complex numbers. So just for our in this course, we are going to focus more on these three or these five type of factors: gain, integral, derivative, first order zero, first order pole. So we have five representation or five graphs. Each one will be sketched individually. Then the combination of them will represent our frequency response using body plot. So the first one is the gain case. Again, we said if your transfer function has a constant number without any variables, I mean, just like numbers 5, 10, 100, 13, whatever is the number. So the case here, or in order to draw the body plot for this gain, we need to draw the body plot for the log magnitude and also for the phase. For the log magnitude, it will be like 20 log k. Whatever is the value of your k, you need to calculate 20 log k. If k is equal to 5, it will be 20 log 5. If it is 100, it will be 20 log 100, or this one in dB. Then you are going to draw it like straight lines. So this is the x-axis, and if your gain give you like 10 dB, so it will be like one line in the 10 dB. If give you like 100 dB, it will be like one line at 100 dB. So you draw it like one fixed or one straight lines in a horizontal straight lines, depends on the value of k. So whatever the value that you give him for k, you just use your calculator, find 20 log this value. Then draw it. It gives you like constant number, so you just draw the constant number on the vertical line here as I mean on the vertical axis point as a horizontal line in parallel with the x or the frequency axis. Then the phase angle of the gain k, we said each frequency response or each body plot consists from two graphs. One is the magnitude, one is the phase. So the phase for the gain is 0. Why 0? Because if you have your value of the gain is equal to 5, okay, if we said k is equal to 5, and we assume this k is a is a number, a complex number. So complex number means it's like 5 plus j g0, correct? If we have 5 only, it means like 5 plus j0. If you want to convert this number or this value from the rectangular form into polar form, so it will be like 5 square plus 0 square or square root. So it will give you the magnitude is 5 with the angle of tan inverse 0 over 5. So it will be tan inverse 0. Okay, tan inverse 0 over 5, it will give you the angle is 0. For that, the phase here is 0 value. For any real number or any constant number, it can be represented by the magnitude as a value here, and then we find its value in dB or in decibel. Then the angle will be 0. Whatever is the value, k equal to 100, also the angle is 0. K equal to 1000, the angle will be 0. Okay. So if we want to draw it on a semilog paper, so if we have the value of k, for example, is equal to 5, which is the gain, I mean, it will not be given as a value. It will be a part of the transfer function. Like, imagine that you have gx, I mean, like this one, gs equal to 5 s plus 1 over s plus 3. I mean, it will be a part of transfer function. So if I ask now, what is the gain? You will say the gain is equal to 5. So how to draw the gain alone? You need to find the value of 20 log k, which is 20 log 5, which is 14 dB. You draw it as, this is 15 dB here. You draw it at 14 dB. As just, you know, you see this, the line here, the black line. This represents our body load for the gain here. Okay, at the 14 dB point. This is for the gain. We call it magnitude in dB. Then we want to draw, as you can see here, the frequency representation is like 0.1, 0.1 here, like 10 to the power of negative 1. Then you have 1, then you have 10, 100, 1,000, 10,000, 100,000, million, and so on. So all these, in Similog, the representation, it will be each 10 lines or vertical lines there represent one decade. So between 0.1 until 1, between 1 and 10, between 10 and 100. So if this is 10, that means this will be 20, 30, 40, 90, 100. Then this will be like, if this 100, this 1,000, this will be like 200, 300, until you get like 1,000. Okay, so this is how to represent for the gain value magnitude. For the gain value phase, it is 0. So you just draw a line at the 0 point of the horizontal line for the phase here. So this is the line at the 0 degree. We said the phase angle will be in the degrees, so this is at 0. If the phase angle, later on we will see some phase at different values, so we are going to draw at the specific value. Why? Because as we said here, tan phi is equal to tan inverse imaginary over real. So imaginary here is 0, real is 5, so tan inverse 0 is equal to 0. So we draw the line of 0. This is how to draw for the first type of, or the body plot for the first part, which is this one, constant number. So whatever is the constant number that you will be given, you need to find the 20 log of this number. Then you draw the value in dB for the magnitude, and the value here for the angle is equal to 0. So this is the first part, or the first factor. The second factor, we said we have either integral. Integral means 0 at origin. That means your transfer function will have value of s at the numerator here. So like s plus 2, for example. So the value of s here, this is, we have a 0 at origin. If s is there, so this is, we call it a pole at origin. It will be derivative. This one is integral. Okay. So how we can draw the second factor, which is integral here, or derivative? The integral will be j omega in the numerator. The derivative will be j omega in the denominator. Okay. So for the integral here, if you want to draw the magnitude, in the case of the k, we say 20 log k because it is a value. But in this case here, we have j omega. J omega means you need to redraw. If you have the value here, then the number, assume that we have, in the case of k, we said k equal to 5, correct? So this k equal to 5, we find it 20 log 5. But in this case here, the value is, instead of 5, it is j omega, but it's not for k, it is for the 0 here. Okay, so it is j omega. J omega here represent the imaginary number or imaginary part. Okay, so if you want to find the 20 or the magnitude of image, if you have j5, for example, what will be the magnitude of j5? If you have complex number is j5, it's like 0 plus j5. What will be the magnitude here in this case? It will be 0 square plus 5 square, all under square root, so it will be also 5. So the magnitude of j5 is also 5. The magnitude of J 100 is also 100. So you are going to find the magnitude here, which is 20 log omega, whatever is the value of omega here. Then the value of omega here will be changed based on the hex axis here, as you can see here. So omega will be changed. So omega can be 0, omega can be 0.1, can be 0.2, can be 1, can be 100, can be 1000. Whatever is the value of omega here will be changed. So we need to draw it in this. If we assume just for the first one decay means from 0.1 until 1. We have 10 values here. 0.1 based on this graphing of this graph here. 0.1. This is 0.2, 0.3, 0.4, 0.5, 0.6, 7, 8, 9, 10, and 1. You have 10 values here, 10 lines if you just count them. So for these 10 lines, we represent here on the x-axis. So we try to find what is the dB value based on this equation here in order to draw a line. So how to find? So log, JJ omega here, 20 log omega. If omega equal to 0.1 and you calculate it by using your calculator, it will be like 20 log 0.1, it gives you negative 20. Then if you put it in 0.2, it will be negative 14, negative 8, negative 6, negative 3, negative 2. If you have omega equal to 1, so 20 log 1, it gives you 0. Okay, that means the value between 0.1 and 1 start from negative 20. Okay, if this here start from negative 20, so this one is 5 dB here, this is negative 5 dB. We have until here negative 15, maybe it's here negative 20. Okay, so start from negative 20 at 0.1, then until 1 we reach to 0. So where is the 0 point? The 0 point, for example, this is 5, this is negative 5, it is in between here. That means we have a line start from negative 20, go up, increase, increase, increase until reach to this point. Sorry, couldn't draw it correctly. We say this is negative 20, for example, or assume this one is negative 20. Okay, assume this one is negative 20. We start from this point, and this one is 0. In between this 5 and negative 5, in the middle here we have 0 point. So at the 1, if omega equal to 1, omega equal to 1, the value is 0. Omega equal to 0.1, the value is negative 20. So in this case, we are going to draw it like this one. 20 and 1. It's like a line with slope. Line with slope between 0.1 and 1. The slope of this line is equal to 20 dB. Why 20 dB? Because it's increased from negative 20 until 0. So the slope here, if you calculate the slope based on the equation said y2 minus y1 over x2 over x1 that you learned before in the mathematics, how to find the slope of the line. So the slope of this line is 20 dB per decade. 20 dB per decade, that means it will increase by 20 dB per decade. Until this point, from 0 to 10, it will reach to 20 again. So if this one is 20, so we have another line here, it will be like this one. 20 dB per decade. It will go with the same slope. Okay, then go up also again here 20 dB, 20 dB, 20 dB. I mean, per each 10 values, it will increase by 20 decibel. Okay, so this is how to draw the log magnitude. For the phase here, in the case of the phase, it will be the angle of J5. If I ask you now, what is the angle of J5? You will say tan inverse 5 over 0. So 5 over 0 is infinity. Tan inverse infinity is equal to 90 degree. That means the phase, here you can see the slope is 20 dB per decade, and the phase here is equal to 90. So if we want to draw for a 0 at origin, we want to draw the body below. So it will be represented by two graphs. One is for the magnitude Lm. It's 20 dB per decade as we draw it before, and also the angle will be 90 degree. So as you can see here, this is how we can represent. negative 20 up to 0. So this is 0 point here. It's from negative 20 to 0.0 here, it's increased by 20 dB because here negative 20, here 0. That means it's increased by 20 dB. From here to the second 10 here, also it will increase by 20 dB. This point here is 20 dB. Then the next point, it will be 20 dB. So it will increase by 20 dB per decay. So the sign is positive, that means it's increment. Increment by 20 dB per decade. This is for the magnitude, and for the angle here, it is positive 90. So this is the 0 point, and the angle for this 0 at origin is 90 degrees. Just draw it as 90-degree line. Any question about this part? How to draw the gain and how to draw the body plot for the integral or 0 at origin? You will be asked to draw such things in the exam. Okay, I mean, you should understand how to draw it manually. I know you may use the MATLAB, but MATLAB only to confirm that your answer is correct or not. But for the drawing or sketching, you need to draw it by using your Similog paper. Any question about this part? Yes.
Can you explain how the slope form again? In halfway, how the slope forms? The table one, the omega and dB. Negative 20 to 0.
This one.
Yes.
Okay. I mean this one. You have the formula here. Then you substitute for the value of omega. We select 10 values here, just like a sample. If you select another 10 value, you will get the same. I mean, if you select the value from 1 to 10, you will get the same. 20 log 1, 20 log 2, 20 log 3, 20 log 5, 20 log 10, you will get the same answer. It will be like 20 dB per decade. I mean, when you draw line, what you need to do, if you want to draw a line between x-axis and y-axis, you need to find what are the value on the x-axis, and you apply the function. You find what the value for the y-axis here for each value. Then you draw like here 1 point, 1 point, 1 point. Then you draw line. I mean, is this 20 dB is drawing from this representation. It's like linear relation, linear. Okay. Okay, thank you. The third form or the third factor that we have here is the I mean, we said the integral, I mean the derivative one. The derivative one means we have one pole at origin. One pole at origin, that means your transfer function, it has s alone here. S plus 3. I don't know why the pen is not working. Okay, s plus 5 and so on, but you have one s there alone, single s. So that means you have a pole at the origin point, pole at 0, 0. So how we can draw the body plot for this pole? We need to have we need to represent the same equation, which is 20 log of the number here. So in this case, if you have 20 log, I mean the formula, or usually for the normal operations for log, if you have log log 5 is equal to if you have log 5 and you have log 1 over 5, what will be the difference? The value of the will be of the 5 or log 5 is the same, only the sign will be changed. If you try just using your calculator, try to find log 5 and try to find log 1 over 5. It will give you the same value, but it will be in negative sign. Okay, so for log 10, for example, log 10 is equal to 1. Log 1 over 10, it will equal to negative 1. So in this case here, since your 0, your pole at the origin here, it will be the same as the 0 case, but with a negative sign. Negative sign means instead of you have 20 log omega, it will be like negative 20 log omega, because only it's become like 1 over omega here. So it will be the same, but the sign here will be changed. as you can see here. So you have the magnitude here, which will be magnitude for g j omega. It will be the magnitude of 1 over j omega. It will be negative 20 log omega. This is the angle, and if we have a table, the same table here, so all the value will be the same, just will be with different sign. Okay, so negative 20 log omega. For the angle here, it will be the same because we have, if you want to find the, the value of the angle for the omega here, 1 over j omega. 1 over j omega can be rewritten as negative j omega. So if the angle of j omega is 90, the angle of negative j omega is negative 90. So the phase here negative 90 and the magnitude is negative 20 log. So in this case, if you draw it, it will be the same, but instead of negative 20, we have here positive 20. Instead of 0, and the 0 point here, instead of the value will be increased in the previous one, now the value will be decreased from 20 until the 0 point. If when reached to the 0 point here, in the first decade, as you can see, this is the first decade. So this is the 0 point. From starting from point 1, it was 20. At 1 is equal to 0. At 10, it will be negative 20. So where is 10 here? This is 10. This value is negative 20. Then at 100, it will be negative 40 and so on. So the slope is the same. The slope is 20 dB, but here it will be in the negative. So it will be negative 20 dB per decade. That means the value, or if you define, if you try to find the slope by using the normal calculation, which is y2 minus y1 over x2 minus x1. So you just calculate what is y2 here. Here, for example, 0, 0. Here is 20 and 0. So you just make 0 minus 20 over 0 minus 0. So it will give you negative 20 dB per decade, which is the slope of this line. Then each 10 or each decade, each 10 values or each one decade, the value will be decreased by 20 dB, 20 dB. This is for the log magnitude. And then for the angle, it will be negative 90 here. It will be drawn as a line as a negative 90. Why we need to do that? Because it's not easy to find or to draw or to sketch the body plot for a complete transfer function. For that, we need to learn how to sketch the body plot for each element, each single element in our transfer function. Then we will combine the drawing into single sketch. Okay, we will see an example later on, but now I want you to understand how to find how to draw or how to sketch the body plot for each element in the transfer function. Now we already learned 3 elements or 3 factors. The first one is the Sir, I need to left class because I need to go to the other place. Shafiq, Ishraf, where? Where other place? You can leave. Up to you. The man, you still see the slide or not?
Yes, sir. I need to drive. I need
It's
to
okay,
drive.
okay.
Okay.
Okay, thank you. Thank you to notify. Others, they leave only. They don't tell that we are going to leave. 5 mark extra for you. Okay, so now, the second element is the derivative here, or the tool at the origin. We learn how to draw it with negative 20 dB per decade, and the angle is negative 90. The fourth element here, based on these components that we have, is the first order factor. First order factor, that means you have a 0 value or you have a bool value, and this 0 or bool represent just a single single bool or single value with the first order equation. First order means the power here only to omega, no omega square. We are not talking about the second order system. We are talking about the first order system. So you have 1 plus j omega in the numerator, so it is a 0. 1 plus omega j omega in the denominator, so it is a pool. Okay, so we will see how we can draw for such factor. As we can see here, in the case of you have it on the numerator, so it will be a 0, as we said, we need to rewrite the equation in the form of the standard form. So you can see here, if you have j omega plus omega 1, I mean, if the original one, j omega plus omega 1, it is like s plus 3, for example. What we need to do, we need to remove this 3 by dividing by 3, so it's become like s over 3 plus 1. In this case, we are going to divide over omega 1, so it will be like g omega over omega 1 plus 1. So this is the first step. You need to convert it into this form. Then you need to draw for that value. So the log magnitude and also the phase. So in the case for the log magnitude, m of omega for this value here, this is a complex number, consists from real part, which is 1, and imaginary part, which is omega over omega 1. If you want to find the magnitude for this complex number, it will be 1 square plus omega over omega 1 square. This is the how we can find the magnitude for this complex number. It's 1 square, so it is 1 plus omega over omega 1 square or square. Now we have 20 log, okay? So depends on the value of omega here, this magnitude will be changed. I mean, if omega equal to 0.1, omega equal to 10, omega equal to 100, and we have omega 1, when we compare omega to omega 1, the form of magnitude will be changed. So we have two different cases here. And from this one, we can understand what we mean by low pass filter or high pass filter. So in the case of low frequencies, that means the omega value is less than omega 1. If omega is less than omega 1, so this value will be very small, like 0.9, for example, 0.8, 0.5, 0.001, 0.003. So it will be very small value. Then when you make it square, it's become also small, because if you make 0.5 square, it's become 0.254. It's become smaller. If you have 0.1 square, it's become 0.1 and then 0.1, so it's become 0.01. So it's become more smaller. If this part is smaller comparing to 1, so this part will be ignored. Okay, so we have square root of 1, which is 1. So 20 log 1, it gave you 0. That means all the value of omega that is less than omega 1 will give you a magnitude of 0, log magnitude of 0. If imagine that you have, this is the frequency line, this is omega 1 here. Based on this equation, for the value of omega which is less omega 1, all the frequency will be 0. All the value will be 0. That means this type of frequency remove all frequencies less than omega 1. So we call it like it's behave like high pass filter. High pass filter means the frequency which is more than omega 1 will be go through. The frequency is less than omega 1 will be cut off, will be removed. Okay, so this gives you 0. Then all the frequency after omega 1, I mean, if omega greater than omega 1, that means this value is greater than that value. For example, if it is 5 over 4, if 5 over 4, it will give you 1 point something. So this 1 point something, make it square, it's become a big number comparing with the 1 value here. So we ignore the 1 value. We still have 20 log omega over omega 1. So for each value of omega here, we are going to generate a different magnitude. So if omega equal to 10, it gives you a value. Omega equal to 100, it gives you a value. Omega equal to 1000, it gives you another value, like we did before in the case of the integral form. So in this case, the value will be like, for the magnitude, it will be like 20 log omega over omega 1. At the point omega equal to omega 1, so it will be like 20 log 1, it is 0. After that, if omega is equal to 10 omega 1, it will be 20 log 10. For example, if omega equal to 10 omega 1, so it will be like 10 omega 1 over omega 1, so 20 log 10, it will give you 20, for example. After, if omega equal to 100 omega 1, so in this case, it will be like 40. If omega equal to 1000 omega 1, so in this case will be like 60. Okay, so it depends on the value of omega, so the value will be changed. We will see how I mean, before that it is 0, but after that it will be like 20 dB per decade, 20 dB per decade, 20 dB per decade. But from omega 1 frequency. Before that, all equal to 0. Not like in the case of the integral. In the case of integral, we said from the first point, it is increase or decrease. As you can see here, it is increase from the first point. But in our case, for the first order here, it's only increase from the value of omega 1. Before omega 1, it's 0. How about the the phase in this case? The phase for this case will be tan inverse imaginary over real. Okay, so the tangent here for the tangent inverse for omega over omega 1 all over 1, so it will give you this one value. So this is tan inverse omega over omega 1. Depends on the value of omega, we will have the value of the angles here. So in case of omega equal to 0, so it will be tan inverse 0, so it will be 0. If omega equal to omega 1, so it will be tan inverse 1, so this will give you 45. If omega is equal to infinity, so tan inverse infinity here will give you 90. So we have three different values for the phase. The first value is 0 at the omega is equal to 0. The second value is 45 at omega equal to omega 1. The third value is 90 when omega go to infinity. That means it will be like this one. This is omega 1. Before the 0 will be 0. Then at specific value of omega 1 here, it will go to, I mean, at omega 1, it will be 45. If we assume this is 45. So it will be like, let's go like this one, 45. Then after that one until reach to 90, then it's go to infinity here. So it depends on what is the value here. This represent 10 omega 1 and here represent omega 1 over 10. So the 2 point of frequency to changeable frequency, crossover frequency here, it's omega 1 over 10 and 10 omega 1, and here we have omega 1. Before omega 1 over 10, it is 0. At omega 1, it is 45. At 10 omega 1 and until infinity, it will be like 90 degrees. As we can see here, this is how we can draw the log magnitude for this function. For example, you have s plus 3. So it's become like s over 3 plus 1, or omega over 3 plus 1, or j omega over 3 plus 1. All the same. Either say s omega or j omega, but usually for frequency response, the representation come with the j omega value. Okay. So before omega, I mean, in this case here, what is the value of omega 1? It is 3, because we said this is the formula here. It is omega over omega 1. That means j omega over omega 1 plus 1. So our case is omega over 3 plus 1. So omega, which is s over 3 plus 1. So the value of omega 1 is equal to 3. So the change over frequency here point is at 3. Before 3, the magnitude is equal to 0. After 3, the magnitude is equal to 20 dB per decade increment. For the case of the angle, before omega 1 over 10, which is 0.3, before 0.3, it will be like 0. This one drawing using MATLAB actually, so it's somehow it's not linear. Then after that, at omega 1, it will be 45. This is the point of omega 1. For example, at omega 1 is equal to 3. So this is 1, this is 2, this is 3. So you go there. This will be 45 value angle. And here we have 10 omega 1, which will be 30. At the 30 point here, 10, 20, 30. This is 30. Start to go for 90 degree. So this is will be like start to change to 90 degree. If we draw it like linearly by using hand, it should be like this one. This is for the case of the pole. For the 0. For the poles, it will be the opposite, just with the angle of with the negative sign here. So we have negative 20 dB per decade, and before omega 1 and after omega 1, it will be positive, or it will be 20 log omega over omega 1 for the highest value, and for the lowest value it will be like 1 plus omega over omega 1 2, so it will be like equal to 0. The difference in this case only the sign. So instead of incremental slope, we have decremental slope. Instead of positive 20 dB per decade, we have negative 20 dB per decade. And for the angle also the same. It will be from 0 to negative 45 and from negative 45 to negative 90, because we have a negative sign in this for the case of them. Okay, so we can see here 0, negative 45, and negative 90. When we want to represent by using the semi-log paper, it will be like this one. This is for the magnitude. It's come to the point, the same here, we use the same example, but here it is in the pool. It's not in the, it's not a 0. So in this case, this will be represented by this value here. It's like this one. You have S will be j omega, and you want to convert this to 1, so you divide it over 1. So this j omega over 3 plus 1. So in order to draw this one, it will be like this one. At the point of 3, I mean before 3, all equal to 0. After 3, it will be negative 20 dB per decade. That means from this point, which is 3, until the point of 30, this point here, this is 30. You can see here, this is 10, 20, 30. This is how to read the graph. 20, 10, 20, 30. So at the point 30 here, it's decreased from 0 to negative 20. So it is decrement by negative 20 dB per decade. The next one will be 300. So it will be at the 300 here. This is 100, 200, 300. I mean, at this point, it gives you like negative 40 dB per decade. Okay, that means it will, each 10 decade it will decrease by 20 dB. So here 20, here 20, so it's become 40. The I mean the 3000 it gives you like negative 60. The 30,000 it gives you like negative 80 and so on. Okay, so this is how we can represent the body plot for each element or each component of our transfer function. The steps are: first, rewrite the transfer function into its standard form. Second, when you rewrite it into its standard form, we are going to omit the value of poles and the value of 0 by divided by this value. So if you have 3, you divide by 3. If you have 10, divided by 10. If you have 7, divided by 7. And also at the same time, the factor or the operator of frequency will be divided on the same value. Then you need to define the different component of this transfer function. So what is the gain? What is the integral 0? What is the derivative pool? What is the first order 0? What is the first order pool? So you need to define the 5 elements here for this case. Then you draw each one separately. At the end, combine all your sketch into one graph. So this what we are going to see in the example later on, when we have a complete example which consists of the different factors or different components of our transfer function. So this summary for all these graphs, as you can see here, it shows you this is like standard form. If you have a gain, you are going to draw it as a magnitude 20 log. As angle, it will be 0. If you have 0 at the origin, so you are going to draw it like 20 dB per decade with the angle of positive 90. Whatever is the value of n here, you need to multiply. So if n equal to 1, it will be like 20. If n equal to 2, it will be like 40. If n equal to 5, it will be like 100. Whatever is the value, so just multiply. For the phase, also the same, it will be 90 times n. Okay. Then if you have the 0 at the poles, it will be like negative 20 dB per decade times n, whatever is the value of n, or negative 90 times n, the same here. If you have first order 0 first order pole, and also this will be the 2 bar. These the 2 that I told you we are not going to cover in this course, which is related to the second order system. So as you can see here, also it can be easily represented by their own components. I mean, depends on what is the value of omega and what is the value of zeta, and because all these variables like zeta and so on are related to the control system. Last time we used for the, we need to use them for the second order system. like damping ratio and natural frequency, whatever is the value. But let us stop here for this part. I mean, for these 5 components, you are required to know how to draw the body plot for these 5 components. Okay, so here also the same. It's a summary from I mean a more clear summary about this one. So this is for the gain. This is for the first I mean for the integral form. This one is for the derivative form. This one is for the first order 0, and this one is for the first order pool. Okay, I mean for this for the second order pool. So this is the table that represent different part of the or different component of the transfer function. Please go through this table, understand how we can apply in our transfer function based on the component. What you require to do, you need to draw such thing for different value, individual value. Later on, we are going to combine all these elements in one transfer function. I mean, if the transfer function include all these elements, we are going to draw it as a one body plot graph. And this will be like what we are going to do in example 1 next class. Okay.